All right, welcome everyone. I guess happy Halloween. I'm not an expert of American holidays. I guess this is the byproduct of being on holiday today, plus homework too. I know you're working super hard on that. I think you're doing a great work. We're listening to your feedback. We learned a lot from this experience, but I think it's also going to be extremely useful for you to learn these very recent techniques. So keep up with a great job. And today we're switching gears in terms of topic. So if you think about it, for the first 5 weeks, we focus on modeling networks, identifying properties of networks, featureizing networks, and finding good features for machine learning tests downstream, all the way down to the last couple of weeks where we went deep into the deep learning revolution, and then we try to see how can we find these features automatically, how can we architect machine learning models that can learn from graphs, both in terms of topology and features. So now the way in which we're going to change the topic today is, for the first time, we're going to try to study dynamic behaviors over the networks, okay? So the title of today's lectures is Network Effects and Cascading Behavior. So what does it mean? You can think of a network as a medium where certain information spreads or contagions are spreading and so forth, okay? So here are some examples which you can think of them almost as synonyms in some sense. If you go and check different research fields, they call them they call these spreading behaviors in slightly different ways. They can be called cascading behaviors, or you can think of diffusion of innovation. So if there is a source of innovation in the network, then this innovation will spread and people will adopt it. They're called network effects. If you're into health, clearly you heard about epidemics, ways in which viruses are spreading and so forth. But overall, what we care about is the behaviors that that basically model a cascade are, and the way in which information spreads from node to node usually resembles an epidemic. Okay, so what is an epidemic? How does it work? And why is it a very interesting problem to study? Here are some examples of where you might have heard about this phenomenon and why is it so impactful. So we already mentioned the biological examples. You can think about how diseases are spreading in terms of sexual transmission, or how diseases are spreading in terms of like flu. So one is coughing, and then the viruses are spreading over airborne. Or you can also think of technological cascades, both in terms of how information spreads. We're going to be talking about memes, and even more recent hot topics. You can think of fake news, the way in which they are spreading very quickly. And especially if you study, for instance, databases, you might have heard about cascading failures. So this idea that if there is a node in your cluster that fails, or part of your transaction fails, then you have to roll back and recover all the operation that has been done. Okay. And last but not the least, there is a lot of work done in terms of social networks, not only in the way in which news and rumors are spreading, but also in terms of viral marketing. And if you think about it, a lot of very large internet companies today are all based on this concept, okay? You can think of Snapchat and Instagram and all these, new phenomena of social networks where being able to influence people through viral marketing is pretty much the main business models that is driving the revenues, okay? So that's why these topics are important on a very wide spectrum of different scenarios. So let's think about an example in terms of media. That's how pretty much the internet has been working since the very beginning. You have some obscure text story, and then there is a random guy who writes about it in his or her small tech blog, and all of a sudden, if this article gets the attention of big verticals like Engadget, Wired, and so forth, all of a sudden this obscure text story catches fire and everyone is talking about it, okay? To the extent that sometimes it can even get media attention from large news broadcasters, okay? So what you're seeing in front of you right now is basically a cascade tree, all right? So from the source of the information, in this case a text story, all the way to how can you reach most of the people, and clearly one of the most powerful media to do that is a news channel, okay? Now, other examples, as I was mentioning at the beginning, this applies also to social networks. So in this case, this is probably one of the foundations or pillars of modern social networks, the idea that not only you can write your own content, and in the case of Facebook or Twitter, you can express your preference, you can tell that person that you like what they were talking about, but you can also share it. Okay, so like you can borrow that content, put it in your feed, and make sure that other people are gonna be reading that. Okay, so if you're a fan of Nutella and ice cream, which I definitely have myself as well, you're gonna go and share and make sure that everyone can taste something delicious. Now, even a more serious example. So this is the standard case of memes. I think I tried to find the most politically correct one out of there because they can be pretty raunchy from what I've seen. Yeah, so you have this funny meme on how you can compute the volume of pizza in a very self-contained form. And if people decide that they love it, they start to share it, and all in a sudden, this catches fire, and a lot of people are reading about it and expressing their love for pizza. So this is a standard case of meme. Now, few of the examples that I just mentioned, they don't have a big impact in terms of revenues for companies. They're more in terms of social phenomenon. Now let's try to think about how viral marketing works. So this is very important, for companies that are selling products, especially expensive one. So what you do is you find a person who's very vocal and has an impact in terms of the opinion that they're expressing, and all in a sudden people will start to listen to that feedback coming from that person and listen to his or her recommendation and say, you know what, I'm gonna buy the same book because I heard it's pretty cool. So in this case we are talking about Freakonomics. And yeah, all in a sudden this product starts to be adopted by multiple people. So, and we're gonna go more in detail about these topics in the next week or so. But basically, this is the idea of how you maximize the influence in a network. So if you can pick the right people that are very influential and that everyone is listening to them, then all in a sudden your product is gonna be adopted very quickly. And not an expert of social media myself, for sure, but I think you can think that if you're trying to sell something in fashion or whatever, and you can get a Kardashian writing about that on Instagram, then all in a sudden everyone is going to be wearing exactly the same clothes for a year or so. Okay, so that's the concept of viral marketing. Now, something a bit more serious. I promise I'm not going to be mentioning Instagram stars anymore. Spread of diseases. So like you have this toy example in terms of Ebola. So this is the, you can think of these, perhaps let's say these are states, and if there are connections, if people are traveling from one to another, so if there is a high likelihood that they're going to be in the same room or in the same city, and then you get this patient zero, okay? So the first person who contracts Ebola. And what we are going to do to study this cascade is, at each time step, you slice basically your data through a timeline, and you find out how the disease is spreading, okay? And why is this extremely important? So that is, in the case of, trying to contain a large contagion, is we don't care only about how it spreads, even though clearly it's extremely important, but we also care to see where it spreads. How can we quarantine subjects? Like, can we make sure that, for instance, from this state, no one is traveling there, so that we try to block the contagion here rather than allowing it to spread even further, okay? So that's why it's extremely important to come up with reliable models that can give us an idea of how Ebola is spreading so that we can try to contain it, okay? And this problem is so relevant and important that I think Bill Gates has been talking about it for the past few years, and it's part of his philanthropic work, and is extremely worried about the fact that there might be diseases that can kill tens of millions of people in just a few months. So that's why he's putting a lot of effort in his foundation exactly to tackle these kind of problems. Okay, and networks here can help to find out how to contain rather than letting it spread widely. Okay, so let's try to formalize a bit more the problem, agree upon the terminology so that from now on we can understand each other better. So the way in which a contagion spreads, first of all, is over the edges of the network, okay? So as we said before, edges and nodes can represent different things, but in this case, this could be just people meeting in the same room, or it could be close by geographical locations and so forth, okay? But once we have this model, we made the contagion spread along the edges. And then what a cascade does is it basically elicits a propagation tree over the graph, okay? So this is our, again, patient 0. We know that the contagion is spreading through these two edges, and then, this node gets the virus, and it keeps on spreading, and so forth. So this is how the contagion has propagated, okay? So basically what we get is we found now the propagation tree for our cascade, okay? So this is the data structure that we're gonna be studying, okay, that we're gonna be taking into account. And to agree on the terminology, what spreads is called the contagion, and the infection event, usually they're called adoption, infection, activation, depending on the scenario. So if you're talking about epidemics, it's clearly infection. If you're talking about products, for example, it's going to be adoption, who adopts a certain new technology. And the main players in our cascade are the infected or active nodes or the adopters. Okay, so people that either are getting the infection or that are deciding to adopt a certain technology, for instance. Okay? All clear up to now? Awesome. Let's move forward. So now, how do we model diffusion? Okay, so I was mentioning it's extremely important to find a relatively simple and reliable model. So what are we going to see today, and what are we going to see in the next week or so? So today we're going to be talking about decision-based models. Okay, and in these decision-based models, what we do is that we are allowing nodes to make local decisions, okay? So you can think about like each node here is a person who decides to adopt a certain technology or not, okay? So we make all the decisions node-based, okay? You can decide, I wanna install this new app on my phone, or I wanna buy this new piece of hardware. These are decision-based models, okay? And in the case of epidemics, instead, this model will not work, right? Most of the cases, no one makes a deliberate choice to get a virus, right? So in that case, what happens is we're going to have instead a probabilistic model, okay, so which we're going to be seeing next Tuesday. And here, we're going to try to model the influence or the disease spreading. And what happens in that case is that an infecting node tries to push the contagion to an uninfected node. And then we're going to be having a probabilistic model there, right? Which tells us, we flip a biased coin, and it will tell us, okay, this person has received the virus, yes or no, okay? So that's why for the case of contagions, we're going to be mostly using probabilistic models. But for instance, today we're going to be talking a lot about technology adoption, and that's more a decision-based model, okay? Or another case, for example, is if you decide to manifest, okay? There is a protest for something that is not working in a country. You make your own decision if you want to be part of it or not. At least we hope that's the case. That's how good thinking people work. They make they ponder their decision before attending or not a certain manifestation. Okay, so let's dive into the decision-based model of diffusion. Now, how are we gonna formalize the problem? So we're gonna be borrowing from very simple game theory models, and throughout your lecture, we're going to try to simplify the problem as much as possible. So we're going to be having 2 players, okay? And I'm going to be explaining you why 2 players are enough to have a model that then can after generalize. And each player in our initial scenario can adopt either 2 behaviors, okay? So you can either be in behavior A or in behavior B, okay? So what is the intuition here is that you're node V, okay? You're part of this UNet here, and you're gonna be gaining more payoff if your friends have adopted the same behavior as you. So, in this case, you have 3 of your friends that have adopted the blue behavior, 2 of your friends have adopted the green behavior. If the payoff for green and blue is the same, then your logical choice is to adopt the blue behavior, right? So, and that's why we can formalize all this model just with 2 players, because at the end of the day, what you can do is that you allow each pair of nodes to play their own game, okay? And so when you have a larger network and you have multiple nodes, you're just going to be playing a lot of different games among all the possible pairs. One could argue that this model doesn't scale to very large numbers, which is absolutely true, because we're going to be seeing a quadratic explosion. But there are a lot of cases where you don't have to run this on a graph where each node represents a person. Rather, you will be doing that, perhaps with demographics or with clusters of people that have a very similar profile. Okay, like that's how you can simplify this graph in such a way that it's gonna still be tractable in terms of computation. All right. Okay, so let me give you some examples now of technology adoption that has happened in the past few decades and how it ended up. I'm quite sure very few of you might have seen these in your life. So these are video cassettes. At the bottom you can see the VHS technology. At the top is the Betamax. And I think this battle started around the 80s. And the clear winner at the end of the day was the VHS technology. They were pretty much offering the same kind of product. If you're curious, you can go online, and there are a lot of people who are claiming that Betamax was strictly superior in terms of tech compared to VHS. I'm not an expert of video, so I can't really judge. But definitely there were people supporting one or the other side for a few years. And VHS ended up winning just because more people adopted it. Okay, so that's how it goes in very large markets, especially in a context where you might have to borrow or exchange your medium. Then the fact that your friends have exactly the same one plays a key role, right? Because this was before the internet piracy, so people were exchanging cassettes to watch movies. So that's why it was very important that your friends have exactly the same VCR at home. Now, a more recent example that instead you might have experienced yourself is this exactly the same battle happened a few decades after. So we had Blu-ray versus HD DVD. And once again, here it was kind of unclear which one of them was the best tech. And Blu-ray ended up winning the battle, and HD DVD pretty much disappeared. Okay, so that's why it's very important to being able to predict what's going to be the outcome of the technology adoption, because to come up with these standards, it costs a lot of money to companies and years to develop them. Okay, so if you already know that each one of them had a bunch of companies supporting the tech, you don't want to be in the losing party here. So you want to be part already of the winning tech, and that's why it's so important to being able to predict these as quickly as possible. Okay, so everything okay? Cool. All right, so let's talk about now our payoffs, okay? So as we were mentioning before, if both like our node B and W are adopting behavior A, then each one of them gets a payoff of little a, okay? So we are the case on top. Then if B and W both adopt behavior B, also in this case, they're getting a payoff. In this case, it will be little b. But now if B and W are adopting different behaviors, then each one of them gets a 0 payoff, okay? It's a very simple game mechanic in here. And as I was mentioning before, when you map this simplistic model into a large network, what we are doing is each node B is playing a copy of the game with each of its neighbors. And at the end of the day, the payoff is just the sum of the node payoff over all the games that node B has played, okay? So as simple as that. Now, let's see how to calculate the payoffs for the generic case of node B, and also let's try to see how node B can make the best choice in terms of its own payoff, its own return. So, oops, here's the case. Okay, so we have our node B, and our node B has D neighbors in total, and a few of them have adopted strategy A, a few others are with behavior B. And we just encode how many are adopting a certain behavior with this probability P. Okay, so with probability P times D, these are the number of neighbors that are using A, and with minus P times D is the number of neighbors that are adopting the strategy B. Okay. Now, what we do is, how do we compute our payoff? Okay, so as easy as our payoff coming from the choice of A. So if B is choosing strategy A here, this is how we compute our payoff, right? So this is, the little a is the single payoff that you get from one of the nodes adopting the behavior A, and then we do P times D, which gives us the number of neighbors that adopted A, okay? So we sum up over all the games on the left side. And conversely, for B, we do exactly the same. Sum up on all the neighbors on the right side times the payoff little b. Okay? So as easy as that. Now, how does B make the choice? Okay? So we need to come up with a threshold, right, which will decide if B goes for A or goes for B. And this threshold is very easy to compute. Okay? So we're going to call it Q. And it's basically the ratio between B and A plus B. So what does this threshold tell us? If it's worth to switch to B, okay, then we need a probability higher than this threshold, so that summing up all the rewards, all the payoffs over B will give up better payoffs compared to the ones over A. Okay? Question?
Sorry, maybe I misunderstood the terminology. I thought A and B were just sort of fixed payoff constants.
Correct. So A and B are fixed payoffs.
I see. Okay.
Yes. So perhaps the thing that is that might be misleading is the fact that so capital B is the behavior that you adopt, and lowercase b and lowercase a are the payoffs that you get with when those two behaviors are matching. Sounds good? Awesome. Question?
Why are you setting the payoff that you get from adopting behavior A equal to the payoff of adopting behavior B, basically? Like couldn't those two sides be different?
So the question is, why are the payoffs for A and B not different? Why are the same? But they are different, right? So we're using different constants here. So if you are matching on the A behavior, then the payoff is going to be lowercase a. If you're matching on the B behavior, the payoff is lowercase b, right? So they are different. They could be the same. And no one is preventing you to have A equal B equal 1, for example, okay? The only thing that here is not dynamic is these payoffs are not changing over time. And you might argue that, hey, this is not realistic, you know, like maybe after some time these payoffs should go down, which is absolutely the case, you know. So you can make this model arbitrarily more advanced, therefore more generalized. Sounds good? Awesome, thank you. Anything else? All right, let's move forward. So let's go through an example scenario. Now we have our graph where everyone is starting with behavior B, okay? So like that's the status quo technology. Let's say like everyone was using Betamax back then, and my pointer is, there you go, we're back. So everyone was using B, and a small set in our graph S is formed by just early adopters of A, okay? So you have this happening in a lot of technologies. You read on the internet a lot about, I don't know, Apple fanboys, you know, people that will buy each single product that Apple releases, okay? So that's our A, okay? All the people that will never buy anything else except Apple products. So we hardwired them, okay? They're gonna keep using A no matter what payoffs tell them to do, okay? They're gonna bring it to their own grave, okay? So this is our A group. And assume that, you know, we tune our payoffs in such a way that a node say, if more than 50% of my friends take A, I will also switch to A, okay? Otherwise, I see no benefit, I'm gonna be staying in B, okay? So basically, we can make A and B so close to each other, you know, apart from a small positive epsilon, and then we say, no, the threshold is just Q equal 1/2, okay? So we need at least half of my friends have to be adopting that technology. Now, what happens in this case? So let's run through a scenario, okay? So our set S here is the set of the hardcore early adopters, okay? So we have node U and node B. They already adopted A, and all the gray nodes instead have adopted B, okay? So how are we gonna compute this, okay? So we said if more than 50% of my friends are red, I'm gonna be turning to red as well, okay? So I'm gonna be adopting technology A. So who can give me some examples of nodes that are gonna be turning to red already? Like, why is this clearly right? So this guy has only one neighbor, and it's a red neighbor, so definitely that node will change. Other ones, node here on top has 1, 2, 3 neighbors in total. 2 of them are red. Boom, switches to red as well. Same for the one on top, 2 neighbors, all of them are red. This isolated node is red as well, and we got this red node. Does it stop here, or does it move forward? What do you think? Exactly. So That's why we think about it as a cascade, right? It's a process that happens over time, and basically the local decisions of certain nodes that decide to swap will influence, as a consequence, other nodes, okay? So there you go. Now we get also, this node all in a sudden goes from a balanced 50% to all its neighbors are red. Same happens for this one, and same happens for the node, for this node at the end of the tail. Now the only two nodes that are not going to be changing are the ones here on top, right? Because since the very start, they had a very balanced situation where one neighbor is red, one neighbor is gray, so they have no incentive swapping, okay? So again, another assumption that we make into this model is that the nodes are perfectly rational, which doesn't always apply to humans, right? So sometimes people change their opinions or they jump to a new technology just because why not? But in this game theory mechanic that we're talking about today, our nodes are perfectly rational, so they're gonna be swapping if and only if there is an incentive for them to do so, okay? And given these assumptions that we just made, you can also understand by yourself why this process is not reversible, all right? So once this cascade starts to spread, once this kind of technology is being adopted, then there is no reason in this relatively simplified model for the nodes to change their state, right? Because they made the decision based on the rational fact that they will get a higher benefit, a higher payoff. So there is, over time, this is only monotonically increasing. Like the number of red nodes is only monotonically increasing or is going to reach a plateau, okay? So that's why you're not going to think that after this stable situation, some of the nodes will turn into gray again, right? Does this make sense? You can simply prove it by contradiction, okay? So you can take a node in isolation, try to see what happens if you swap it to gray, back to gray, and what it will do is it will flip again the next stage back to red, okay? All good? Okay. So now that we have seen the model, let me try to give you a real-world example so that we're going to be talking about something that you can easily relate to. And the paper that we selected is a publication from 8 years ago, and what it does is it tries to model protest recruitment on social networks. And I've been talking about this topic with many of you because you were interested in terms of projects. So here is why this topic is very interesting. So this paper goes through an event happened in Spain in May 2011, and it was an anti-austerity protest. So what was happening back then in Spain, if I recall correctly, is there was a huge financial crisis, which happens very often in the Mediterranean Europe. I'm part of it as well. And back then, 25% of the people were unemployed, okay? Possibly something you never heard of in the US, but this happens in Europe, okay? So after a certain threshold, people said, we cannot go on anymore like this, okay? And what they did is, Twitter was relatively early stage back then, especially in Europe, there was not a huge adoption, but people decided to use it to organize and mobilize users to participate in the protest, okay? So clearly, the government had to receive the message from all the people, running on the streets and expressing their discontent for what was going on. So how did they organize this, and how did the authors design their study? So what they did is they manually selected 70 hashtags that were used by the protesters. So they went through a lot of tweets, and clearly the authors were able to speak Spanish. I know there's also Italian Revolution and a lot of other Spanish words in there, and they selected the key hashtags also over this timeline. And if you go back and check the paper, you will see like each one of them corresponds to a certain exogenous event, the beginning of the protest. And I think, in a couple of these dates in the timeline, there were some reactions from the government, so like each external factor contributed to a different spread of the information in the Twitter network. So they selected these hashtags, and then what they did is they collected relevant data, right? So they searched and they crawled this 1 month period, and they took all the tweets that contained those hashtags, and they ended up with roughly 6,000 tweets in total, okay? And not only they collected the tweets, they also collected the relevant users, okay? So basically any user that tweeted relevant hashtags, and not only them, but also their followers and followees. In case you never use Twitter, it's an asymmetric social network, which means you can follow someone, but they will not necessarily follow you back, okay? So that's why for each user, you need to take the list of followers and the list of followees. And in total, they ended up with almost 90,000 users, okay? So when I was mentioning to some of you to perhaps reconsider your very large project on Twitter, is because back then collecting this data was not trivial, but still relatively feasible. Today it's much harder to collect such large data sets focused on specific relevant data because one of the business models of Twitter now is to sell you this data. Okay, so that's why I try to steer away from some of these projects. Okay? Not because I don't find them interesting, but I didn't want you to get frustrated. So now that they also collected all the relevant users, what did we do with these connections? Okay, they created two different networks. Okay, so one was a full network with all the Twitter follow links, so as a directed graph, and then they also tried to create more compact and a network with a stronger signal, which basically was the symmetric network. So I told you that Twitter is inherently asymmetric, but what you can do is you can keep only the users that have a reciprocal follow, okay? So you have node I and J, you keep a link only if I is following J and J is following I, okay? And out of this data set, you're building an undirected graph, okay? And these are basically the strong connections. And we're going to be seeing why having these two different graphs is interesting, because they play a role later on in the analysis, okay? Now, a few definitions, and which we are going to be carrying over, especially when we see the plots, okay? So as we were mentioning before, we need to know about the players in a contagion or in a cascade, and we need to know about their activation. Okay, so we need to know when they become active. So in our case, an activation in this study means the first moment when a user starts tweeting protest messages. Okay, so whenever a tweet contains a certain hashtag in our set of 70 hashtags, they become an active user. Then we have Cascading, which is the total number of neighbors when a user became active, so all the neighbors that a certain user has on Twitter, and then Cascading, which is the number of active neighbor when a user became active, okay? So what is the activation threshold? It's nothing but the ratio between Cascading divided by Cascading. So out of all the neighbors that you have, how many of them were active when you decided to start tweeting about the protest, okay? So intuitively, you can think if someone has a very low activation threshold, is a person who doesn't need a lot of external input and a lot of peer pressure to believe that this protest was interesting, was important, okay? Conversely, if most of your neighbors are tweeting already about the protest, it means that you have a very high activation threshold, and it will become part of it only after you're sure that everyone is interested in it as well, okay? So that's why this simple value is extremely important, okay? It basically gives you an idea of how quickly a certain cascade will spread, and what is the likelihood that that cascade will spread, okay? Now, you can also think about the fact that this activation threshold is definitely changing depending on what cascade we're talking about, right? So say you're a Spanish citizen, this activation threshold might be very low for you, right? Because you care about your country and you want to make sure that everyone gets a job. Conversely, if you are a Spanish citizen, and we're back to the meme about how you compute the volume of pizza, your activation threshold might be much higher, right? So the reason why I'm highlighting this part is the fact that these values are very much specific to the study or to the scenario that you're talking about, okay? So there is no magic threshold that you can apply to each cascade phenomenon, okay? You need to find it, and you need to figure out the distribution for each one of them. Okay, now let's go and see the different recruitment strategies that they had. So this is basically putting in numbers what I already explained you. So if the ratio is close to 0, then our user will join the movement when very few neighbors are active, no social pressure in that case. And if you can think that if that ratio is exactly equal to 0, then that person is one of our patient 0 in the case of the epidemic, or in the case of the protest is the person who started the movement. So the person who came up with the hashtags, or the person who wrote certain articles online, and then he or she decided to write about it on Twitter, and people started to adopt it and started to spread the information. Okay, so those are the people who are initializing the whole process. And conversely, when it's close to 1, we said these are the people who require high social pressure before they become part of it, okay? All right, now let's go and check the distribution of the activation threshold that has been found by the authors of this study. So interestingly enough, it's mostly uniform if you think about it. So let me tell you first of all what's on the axis. So on the x-axis, which goes from 0 to 1, we have our activation threshold. So it's k sub a divided by k sub in, and on the y-axis, basically we have the probability distribution of our activation threshold. And interesting enough, we see that there are mainly just 2 spikes in this distribution, which is otherwise almost uniform. And the first spike are the people with very low activation threshold. Okay, so as we said before, we need some self-active users to allow this cascade to start. Okay, these are the people who are making the rumor at the beginning. Okay, we're talking a lot about it. And then they also find another spike around 0.5, which means many users join after pretty much half of the neighbors are doing so. Now, clearly, these are not 2 isolated spikes. It's not a clear cut. I need 50% of my neighbors, otherwise I will not become part of it. But it means, after you start to see those hashtags and those articles appearing oftentimes on your Twitter feed, then you're going to start to talk about it. Okay? And clearly, you see this drop in the distribution towards the end, because these are the people with the highest degree of social pressure required to become part of the protest. So this was the first takeaway. Once again, you will see very different distributions when you study different kind of cascades. And the other interesting one is, what is the effect of neighbor activation, of the neighbor activation time? So here the hypothesis is the following: if several of my neighbors are becoming active in a very short time period, then a user is more likely to become active. And intuitively, what this is telling you is, if people are very vocal about this protest, and all in a sudden everyone is talking about it, even if it's still the minority of the Twitter user base talking about it, you have higher chances to become part of it, okay? Because you feel the sense of urgency. And this sense of urgency is basically encoded in what is the burstiness of the active neighbors, okay? So the way in which you compute this burstiness is basically taking the activation level at time t plus 1 minus what was the activation at the previous step, and then you divide it by the current activation level, okay? So pretty much by taking this derivative on that spot, we find out what is the burstiness, and the higher it is, the higher chances you will have to become part of it. Now, this doesn't apply once again to all the users, right? Because otherwise, we wouldn't be getting the start of this cascade at all. So as you can see here, people that have low thresholds are insensitive even to this recurrent burstiness, okay? So this is our low threshold, remember before, around 0.1, 0.2. These are the people that don't require that kind of burstiness for the recruitment. And then on this side, we find all the high threshold users that are joining after there is a sudden burst of activity in the network, okay? So yet another interesting factor, which is not only how many of your neighbors have to be active, but also how quickly this has to happen in order for you to pay attention to it, okay? Awesome. So now in this data set, we started to talk about cascades. We cared about this cascade tree, and so we want to analyze what are the properties of this tree, how big it is, how often does it happen, how often does it die very quickly. And this data set doesn't have cascade data, right? I mean, no social network data set, for example, will have a cascade data. So we are just given the data, and we're just given the behavior of the single users. But it's up to us to extract the cascade information. So how do we do this, okay? So the cascades in this case were identified as follows. So if a user A tweets a message at time t, and then one of its followers tweets a message at time t plus delta, then they're forming a cascade, okay? So what you do is, here for example, is you divide your timeline in uniform blocks, and then you go and check if the information is moving from one user to another, and if this spread doesn't stop, okay? So in this case, for instance, we study the cascade over 2 time periods, and we see, okay, it starts from user 1, it spreads to some users that don't adopt it, but then it spreads to 2 also that adopts it and sends it over, and then all of a sudden it reaches user 3, it was super connected, everyone is reading his or her feed, and then the cascade starts to spread, okay? Now, conversely, there is also a chance that, if, say, 2 didn't catch this tweet here, then the cascade will die right away, right? So what we're going to see right now is that not all the cascades are going to be successful, okay? So most of them are going to just be dying very quickly, okay? So there is not a single cascade that has mobilized all the people in this pain manifestation. Rather, there were a lot of them. Some became successful, and then they were, powerful enough to make sure that people will hear about the problem. So here is how you can analyze the success of cascades and how they did it. The property that the authors focus about was the size of the cascade tree, okay? Which is not necessarily the only property that you might want to analyze, but it's definitely the most intuitive one. You want to see how many people are retweeting or writing about a certain hashtag after a person has tweeted about it, okay? So as you can see here, so on the x-axis we have the size S of our cascades. So this is a log-log plot, and clearly there are just few of them that are extremely successful and very large, but then as usual there is a very long tail of short-lived cascades that are still happening, okay? So this sort of reflects the intuition that we just had before, okay? Any questions? Okay, all good. Now, another question that we might want to ask is, who is starting a successful cascade? Like, can this happen with every single person in the network, or is there a higher likelihood that it will happen with certain specific players in our cascades, okay? And as this slide is already spotting the answer to my question, clearly this is happening more likely with specific people. So how did they study this? How did they conclude that it was the case? They applied a K-core decomposition on our cascade graph. So let me explain first of all what is the K-core decomposition. So first we go through the definition. It's the biggest connected subgraph where every node has at least degree k, okay? But the way in which we do this K-core decomposition is incremental. So if you didn't pay attention too much to that definition, you might think, okay, why isn't this exactly the degree distribution? Can anyone give me an answer? Do you think it's exactly the same, or you expect them to be two different definitions, right? So like, this is the one core, okay? And for example, this node has degree 2, right? So you wouldn't expect that to be just a degree distribution. Yeah?
Yeah, I was going to answer.
Awesome, okay, I just ruined your... Sorry for that, okay. Okay, so that's the first intuition, right? This cannot be just the degree, or like the degree centrality. Sometimes this is called degree centrality, okay? It tells you if a node has higher degree in the network, then clearly that encodes some higher centrality, which means it has a more important role in the network. But that's not exactly what the K-core decomposition is capturing. Rather, what it tries to capture is there a connected subgraph in our graph that where each member has at least degree k? And the way in which we construct that is we start from basically the periphery of the graph, so from the nodes that have the lowest degree, and then we treat this as an onion, okay? And we just peel it. We peel one layer at a time. So the first layer that we work with is the one core. Okay, so we have this node, degree 1, all these nodes with degree 1s, we're dropping them. Now, once we drop these nodes, for example, this purple node that previously had degree 2 goes back to having degree equal to 1, right? So that's why this node is still part of the 1 core. Now, once we jump to this green node instead, I know the second run where we try to peel the 1 core, even if we remove this purple node, all these green nodes will have degree 2, right? So that's why they're part of the 2 core, okay? And you can just keep on doing this incrementally until you get stuck with this 3 core where all these red nodes have at least degree 3, okay? So that's why we work with this concept of K-core. The reason is it doesn't only count to have a lot of, to have a very high degree, so to have a lot of people following you. You also want to be part of this network where a lot of other influential people are connected to you, okay? So that's the difference between degree centrality and K-core. The fact that not only you have a high degree, but also they have a very strong connectivity to other nodes that have very high degree, okay? So that's the intuition of what the K-core is capturing. And so in our case, these are the nodes that we expect to have the most important role in a cascade. So how do we map now this concept into the actual data that's been observed by the researchers? So what they did is they took a slightly larger graph compared to our toy example, and they applied this K-core decomposition. And what they found out is that the red nodes have higher likelihood of starting successful cascades, okay? Now, it doesn't mean necessarily that a cascade cannot start from one or the more peripheral node if it has been especially seen by one of the red nodes, but there is a higher likelihood that this happens from the red part. If you're doing anything like this in your project, I'm totally fine if you try to visualize it, okay? But you should definitely do this in an analytical way, okay? So this kind of representation is not extremely helpful if you think about it. So it gives you an idea that these nodes might have higher K-core values, but make sure that you plot a distribution where you show me, okay, this is the likelihood of a node being part of a certain K-core to produce a successful cascade or not, okay? Question?
Like whether it matters to start a cascade in like a very like high K-core, like high K, but is it like enough to just like for the cascade to just like reach like a very inner K-core?
Yeah, very good question. So you're asking, did they only study the correlation between being part of the K-core and having a successful cascade, or did they also try to study what happens with the peripheral nodes? The answer is, from what I recall, no. But the intuition here is you can already see it from the visualization. Some of the nodes that have started a successful cascade are here in the periphery. So we already know the answer, right? We know that it doesn't happen exclusively in the K-core. And one of the intuitions is exactly what you said, is not only in terms of if you're already part of that, but it's also a matter of how quickly you can reach certain higher, the most important cores of the network. And the reachability sometimes is just a matter of sheer luck. If someone is taking a look at it, or you choose the right hashtags, that's why a lot of people spend incredible amount of time in social networks to have this humongous list of hashtags, is because they're trying to maximize their reachability. And I think that's one of the main skills of marketing people, from what I know. So there's definitely some scientific aspects out of the work that they do. It's not only by chance. Any other question? Yeah.
While they're using like K-core centrality,
Sorry?
While they're using the K-core decomposition centrality, like PageRank could have also worked with like.
Okay, very good question. Why are we focusing on the K-core centrality and not on PageRank or any other centrality measure? Short answer is K-core is intuitive to understand. It's relatively easy to compute, and it's a deliberate choice. So there are, I'm not sure if this year we're gonna cover the lecture on all the different centrality measures that people came up with on graphs. We definitely did it last year, so if you're curious, you can go and check the slides. I would be very surprised if by plugging in a different centrality measure, we wouldn't be finding a very similar correlation. And as a matter of fact, there are a lot of studies that show that PageRank with certain graphs has a very high correlation with just centrality on a graph, okay? So in that case, you will find the same result. And last thing is, here we are working with the fully connected graph, where each link is only if two people are following each other. So it's an undirected graph. And as you recall from Tuesday, the magic of PageRank is the fact that it is able to capture the incoming links and give them more importance. So it will be like using a cannon to shoot a fly in this case, right? Because you wouldn't be able to use all the information in a directed graph. Great. Question?
Yeah, so you talked about users who have low activation, so that means like not that many of their neighbors are doing it, but they're doing it. And then you talk about users who have high activation, which they start doing it after a lot of their neighbors are doing it.
Correct.
Is there a cascade analysis of users who don't start doing something, even if a lot of their neighbors are doing it? So like the opposite.
Great question, okay.
Yeah.
So the question is, has anyone ever studied users that suffer a lot of inertia, basically? Like a lot of people is already talking about that, and they still don't adopt or help that cascade. So I've seen a few studies about that. I'm kind of skeptical, and the reason is, especially from the outside, if you don't have all the activity data from a social network, it's extremely hard to distinguish a user that deliberately ignores a certain cascade versus a user who's just completely idle. Okay, because you know that there is in all these social networks there is a large presence of bots and fake accounts and whatnot. So it's hard to find out if it's not even a person maybe matched to the account. So maybe that's why they didn't follow that cascade. Yeah, so that's one of the problems. Like all these studies are called observational studies, and they're extremely exciting for researchers to perform. But it's always, as you're working on a minefield. You can do a lot of missteps that completely invalidate your findings. So that's why sometimes you cannot ask questions that are extremely cool, just because you wouldn't have the data to back your conclusions. Okay, thanks for your question. Great. Anyone else? Okay, let's move forward then. So, what have we seen? We've seen cascades on Twitter, so real-world example. We've seen that the activation threshold in this case was almost uniform, and we just found a couple of local peaks, mostly matched with people that don't require almost any peer pressure, or people that require at least like 50% of the neighbors to be active. We also seen that most of the cascades are short. This is very intuitive. A lot of them will just die very quickly. And the successful cascades are started by central, more core users in this case, but as we discussed, you can find a different centrality measure here, and there is a high chance that you will find also very similar correlation levels. Okay, so this is to wrap up our observational study on Twitter, and let's quickly recap the model that we use. So we said we are using a decision-based model. It's completely based on utility. Okay, so like each node decides on its own if it wants to be part of the contagion or not, just based on what is the payoff, and it's deterministic and rational. Okay, so there is no random component there that someone will change their mind abruptly, and it's also node-centric. So basically, a node observes decisions of its neighbors and then makes its own decision. All right, so we can make this scale relatively easy. Now, how can we extend this decision-based model to multiple contagions? Okay, so this is going to be the rest of our lecture today. And the reason why this is important is, if you think about it, having only two behaviors is extremely limiting, right? So the reason is you might have concurrent cascades going on, or you might have multiple technologies that you can adopt, or you might even decide to adopt two technologies at the same time, right? So that's why we want to extend our model to make sure that we can support multiple contagions. So what we're going to do in this case is we're going to be allowing people to adopt both A and B, all right? So far what we've seen is the payoff is only in the case when the two behaviors are matching, okay? So we said two A behaviors are giving us lowercase a payoff. B and B give us a little b, and A and B get us 0. But now there are some counterexamples with relatively low inertia where you could be adopting both technologies, for instance. So in the case of communication software, you can decide to install Skype, WhatsApp, or all the other 100 messaging systems that come on mobile phones today. And this only comes with a small hindrance of possibly using more memory on your phone. So it's seen very often that people use multiple apps. Or even in a case where the barrier is slightly higher, so that involves actual cost, there were people back then that had both VHS and Betamax. Okay, so you could have 2 VCRs at home, and then you were able to borrow and get movies from all your friends, no matter what kind of technology they adopted. Okay, so that's why generalizing this model is important, because this kind of scenario happens very often. Okay, so what are we going to do? We're just adding an additional strategy. Okay, so we're back to our simplified model, but now we add the A/B strategy. All right, and with the A/B strategy, what happens is that if your neighbor is adopting A, then you just get the little a reward. If your neighbor is adopting B, then you get the little b reward. And if both you and your neighbor are in the A/B behavior, then you're getting the max between A and B. Okay? So once again, recall that we can always generalize this model. We are just thinking about the local game between 2 players, and then what we're going to be doing in a real network is we play this game with all the neighbors, and we sum all over the payoffs. Okay, so that's why we can analyze it from this very narrow point of view. Now, not only we're going to have this additional matchup, okay, in terms of a different payoff, but we're also going to be introducing the concept of cost. Okay, so there is a certain cost for maintaining both the strategies, and as we said before, cost could be more memory used on your phone, or buying both the VHS and Betamax VCRs and so forth. Okay, so we're going to be introducing also this additional variable in our study. Okay, and the way in which it works is, so a node can receive the payoff A and payoff B from another neighbor by playing A/B, but he has to decide, or she has to decide, if this is worth based on the cost C. Okay, so maybe by adopting A/B, your payoff goes up, but if the cost is not justifying your change of behavior, then this wouldn't be the rational choice for that player. Okay, so that's why it's not as simple as computing the max again, but we also have to take this cost into account. So let's go through a visual example now, and let's see what happens. Okay, so all the examples that we're going to be seeing now are rather simplified. So we're going to just have these chain graphs. Okay, so all nodes, and they're just connected with 2 neighbors on the side, and we have this infinite network which starts with B. So like you can think everyone on my right side here as a B behavior. Then we have our set of hardcore A adopters. Okay, so our fanboys, they're hardwired to adopt A, and they're never going to change their mind. And we're going to run our model over time. Okay, so as we did before, we have different time steps, and we record who changes their behavior given the new payoffs. Okay, and here, once again, each node selects the behavior that optimizes its own payoff. Okay. Now, let's think about here. Okay. So in this case, A and A are getting payoff A between them. In this case, here A and AB, the payoff is A, and AB next to AB is selecting the max between A and B in terms of payoff. But both of these nodes, being the fact that they adopted AB, they're also paying a cost C. Okay. So we always have to do minus C to remove the cost. Okay, and from this side, when AB is matched with B, then the payoff is B. So how will our nodes switch from B to A or to AB? Okay, so how can we study the evolution now of this infinite chain graph? And to do that, what we're going to be doing is we're going to start by plugging values to our payoffs and see how the network behaves. Okay, so in this case, what we're doing is our payoffs are A equal 3, B equal 2, and the cost is equal to 1. Okay, and keep in mind that both A's are hardwired. So in this case, on this side, the payoffs is 3 because they're matching. And then there is clearly this situation where A and B are getting no payoffs. So you can expect something happening in there. Can anyone give me an idea of what would happen here? What would be the first step of the change? It's relatively easy, right? So these two nodes, we cannot touch them. These two nodes are pretty happy. No, they're both getting 2 as a payoff. So clearly something is going to happen here, right? So we want to make sure that B here as a payoff. And the obvious choice here is that B will swap to AB. Okay? So we'll get 3 as a payoff from this side, and then we'll get 2 as a payoff from the B side, still paying -1 as a cost. Okay? Now, what do you think will happen now? Like, do you think there is a next step, or do you think we reached a plateau and nothing is going to change again? Just wrap your mind around the problem for a second. And
if there's a tie, so it seems like if now the next B adopts A, that its payoff doesn't change.
exactly. So if there is a tie, great answer. If there is a tie, as it is in this case, because AB is getting 4, the rational choice is not to change behavior. Okay? So we're stuck. That's the only thing that changes, right? The cascade is not propagating down the chain. Okay? Good. Now this is not always the case. Okay? So this happens only because of the choice we made for the payoffs. Question?
Isn't the global optimum here for everyone to just choose A?
Isn't the global optimal for everyone to choose A? Sure, but the way in which we model this is we make local choices, right? So to reach the status that you said, which is the global optimum is everyone switches to A, there should be an agreement upon all the nodes to switch all of a sudden to A, right? And this is not how adoption works in the real world. So that's the same as saying there is an expert who explains everyone that it's very important to have vaccines and everyone should vaccine their kids, but then not everyone makes that choice, you know. So exactly the same context. You know, it takes time to spread and to convince people, and that's why we reach this static situation where nothing is going to change again. Yeah, but great insight. Thanks. Okay, so I already spoiled what we're going to do next. Now we change the values, right? So as we said here, the cascade stops. Next example. So we change A equal to 5, B equal to 3, and our cost is 1. Okay? So the starting point is similar. It's just that the payoffs are different. So the first step, you can already imagine it. Our central node has to change. Okay? So there is a payoff. Now A equals 5, 5. And the total payoff here is going to be 7, right? Because it takes 5 from the left, 3 from the right, then it's paying 1 in terms of cost. Now, what happens next? Want to give it a try?
Yeah, the one that we were debating about earlier is not a tie anymore.
Exactly.
The second to the right is going to switch to AB.
Exactly. So now this node is switching to B, right? Because currently it has 6 in total as a payoff, but switching to a B all of a sudden brings us to 7, right? We have 5 plus 3 minus 1, so we got AB. And now this allows the cascade to spread, okay? So with just that small change we have done on the payoffs, you will see that now these nodes, you know, the AB node, which currently had 5 on the left and 5 on the right, because here, recall, we're getting the max between A and B. So we do 5 plus 5, 10 minus 1, 9, but the best strategy here is just to straight switch to A, get the full 10 as a payoff, and as you can imagine, you generalize this case, and all the chain will turn into A, okay? So with a little change of payoffs, even if before as well, the global optimum would have been everyone switches to A, in this case, the cascade happens, okay? So, and it never stops. How can we generalize this case, right? So we like models that we can generalize and, you know, where we can adapt them and we can find out what happens with different choices of our payoffs, okay? So how do we generalize it? Again, we have an infinite path. Everyone starts with B's. We have our set of our core adopters of A, and the payoffs that we're going to set are the payoffs between A's is equal to A. Now we're gonna have a fixed value for the payoffs of B, okay? And the reason why we can do this, if you think about it, payoffs can always be expressed as in a proportional way. Okay, so if we fix B to A, then A can be 2 times B, 0.5 times B, and so forth. Okay, and by fixing that value will help us then to find an analytical solution later on. And so we said the payoff A is A, B is 1, and then when AB is going to be A plus 1 minus C, okay, minus the cost that you're paying. Now, for what pairs, so for which choices of cost and payoff A does A spread over our chain network, okay? And the node that we're going to start to analyze first is going to be W, okay? So we need to analyze these two different cases, okay? Based on the values of A and C, what would happen if the starting node here on the left is A, or what would happen if the starting node here is AB, okay? And W is our variable node, and we want to go and characterize what's the behavior of that node, okay? All clear? Awesome. Let's move forward then. So as I promised, now we're going to have a more analytical solution. So now we are in the case AWB, right? So always keep your eyes on the top right so that you know in which case we're studying. The payoffs, we clarified them already. Now, what does node W adopt in this case, okay? On the x-axis, we have the A payoff, okay? And on the y-axis, we have C as the cost, okay? And these are the values for 1. So how are we going to solve this, okay? The first one is we basically make B and A match, okay? So we say if the A payoff is equal to 1, then it matches the payoff of B. So this is kind of a limbo state, right? So it's a tie. If the only two players in our networks were A and B, if that's the payoff, nothing will change because everyone is receiving exactly the same, okay? So we should expect different behaviors between being on the left or the right side of this segment. And similarly here, what we do is if we fix the cost to 1, then we can substitute it up there, and then what we get is that basically cost equals to 1, it cancels out the payoff of B, and then we're left just with the A payoff, right? So because we do 1 minus 1, and then we'll just get with the payoff A, okay? And that's, so once again here we expect different behaviors. And last thing, so we can analyze AB versus B. So in this case, basically we have the cost and the payoff growing with the same value. So they're gonna be canceling out each other, okay, as you can see on top. So A minus C, so they will get to 0, and then we're just left with 1. So we're just left with this linear, so we're left with this division of the quadrant into perfect splits. Okay, so let's go now one case at a time. So when the cost is above 1, okay, and the payoff A is smaller than 1, then the rational choice is to stay with B, right? So let's go up and think about this example again, okay? So I'm here. I have to make a choice for my node W. So my payoff with B is fixed to 1. If I switch to A, my payoff will be smaller, okay, because I'm on this side of the axis. And switching to AB would be even worse because I will be paying the cost C, okay? So that's the first choice that we make. Now, what do you think is here? So only difference is the cost goes below 1, okay, but A is still bounded, is still less than 1. What do you think is the choice that node W will be making in that case? Anyone wants to give it a try?
AB.
B?
AB.
AB? It's B. Okay, let's go through that so that you can see that. So, say this was AB, right? So what would happen is that will be our payoff, okay? So A plus 1 minus C, but here we are in the case where C is always larger than A, okay? So that quantity will be less than 1 in the end, right? Because we are doing 1 minus, plus a negative value, so the resulting payoff will be less than 1, okay? So that's why, once again, staying with B is the right choice, okay? It's not worth it. I know, once you wrap your mind around the way in which this is split, then it's very easy to visualize how the nodes will change, okay? Now, conversely, once we start to have a better payoff for A, then in this area, it's better to switch to AB, okay? And if you think about it, this is sort of the buffer situation that we have seen before. Let me just go super quickly back to where we were, okay? You see in this case where we have these ABs that are carrying over and that are helping us to spread A, okay? That's exactly the situation where we are in that graph, okay? Let me go back quickly here, okay? So here we're in a case where the cost is low, okay? And A is a great product, let's say, so the payoff is higher, so it's worth to swap to AB, okay? And then same happens there. You will go through the numbers and convince you very quickly. And as expected, when the cost is much higher, so when the cost is higher than 1, but then the payoff of A is higher, then the best strategy is to swap straight to A, okay? So why is this interesting? Not only because we can find a generalized solution on how these, which kind of behaviors this node will adopt, but in a few minutes I will show you why this is important also for marketing, right? Because basically, depending on which part of this quadrant you are, will kind of determine how your marketing strategy should look like, all right? Like in this case, it means that your product has to be so good that regardless of the fact that it will cost people to switch, they perceive the payoff to be so large that they don't care. So they just spend the money and they're happy to swap to A, okay? While in this situation, like clearly if you have a new product, you don't want to be here, right? Because no money is going to change. So your perceived additional value is so low, so your A payoff is less than 1, so no one will bother about what you're doing, okay? So at the very least, if you have a startup, you want to be here, right? You want to make sure that people perceive that you're better than A. But in here, to win, what you have to do is you have to have something so much better that no matter what is the additional cost you're paying, people adopt, okay? While here's sort of a penetration, like a penetration strategy in the market. You can slowly start to steal people, from the user base. So they will use both technologies. They will use both Skype and WhatsApp, and then they will find out that they like one of them more than the other, and then they slowly start to abandon the other technology, okay? So that's how this maps to real-world marketing in some sense. All clear? So to make your life easier, we put numbers down in the slides, okay, so that when you want to go through the example, you can convince yourself why everything works correctly in this way. And let me go very quickly to the next example where instead of having A on the left, we have AB, okay? So we're already in the case where the AB buffer is moving, and we want to find out what's going to be the choice of W. And here, it just changes slightly because to distinguish between B and A, basically our split line will be over 2. And the reason is, so there will be a payoff. There will be a payoff for A equal to 1. Sorry, there will be a payoff in total equal to 2 because we have A plus 1 minus C, okay? And same here, our cost there is equal to 1. So AB versus A basically tells us if if the cost is equal to 1, it will cancel out the 1 payoff from B, then you're just left with A. And last thing is here, so in this case, we have our line starting at 1, because when the cost is equal to 0, okay, and the payoff for A is also and the payoff for A is equal to 0, then we're starting for 1, okay? So same story as before applies. You see these two areas where it's worth to stay with B. You have this large area here where it's worth to swap to A, and then you have this buffered zone that we map to what we've seen before, that where it's still worth to stay with A/B, okay, with that hybrid strategy. Okay, same numbers as before. You can just plug them in. It's simple equation substitutions, and then you will see why this is the analytical solution for the model that we have. And with the few minutes that I have left, I just wanted to show the intuition that we had before. So you can even join these two plots that we were using, okay, just to find a generalized behavior of what would happen if your starting node is either A or AB. And so in this case, once again, we know that if your perceived value of A is below the payoff of B, then the technology will not be adopted. In all this area, the technology will be adopted for sure. And in this area, you have a slow transition from B to A. Now, a question that I want to ask you, which I think would be interesting, is what do you think happens here? So if you think about it, on the y-axis, we have the cost growing, right? And with cost growing and the payoff A being between 1 and 2, you will change behavior. You will have 3 different cases, right? You will have a case where your technology is slowly adopted with this transition. You will have a case where nothing happens, so you're stuck in this limbo. And you have a case where A is adopted, okay? So what do you think happens there? Like, can you think of some examples where this happens in the real world? Okay, let me give you some hints. So think about this could be like having different search engines. I know this probably doesn't apply anymore nowadays. Possibly Bing tried to do that with Google, but back in the days when you had multiple search engines and Google wasn't exactly still the leader, we're all using multiple search engines at the same time, right? Searching in different of them, picking out results, and then slowly, you decide to slowly drop one, and then you're back to use Google at the end of the day, okay? So you're in this kind of limbo state, but eventually at least it transitions. Here, if it costs so little to adopt both technologies, and there is no clear winner, no one will become the leader of that field, right? So in some sense, if you think about it, there are cases where prices are inflated. I'm not going to talk about companies because I think this lecture is recorded. but so that's why marketing people can be so genius in some sense, because they know when to overprice things in such a way that it will force people to make a choice, if you think about it, okay? Like, they would say, okay, the payoff is not that much bigger, right? Okay, so we are still bound between 1 and 2. If what you're doing is super amazing, then you're gonna be here and people will adopt it right away, okay? But if you're aware that you've just done an incremental improvement and you're kind of stuck in this area, so if your cost of adoption is so low, people will not bother making a choice, right? Okay, so it's better to jump from here to there, okay? At least you have a chance of being adopted or burning and trying to do something brand new from scratch, okay? So that's why it's cool that these concepts are not only about cascades, but also apply to real marketing, okay? So I invite you to think about it. Okay, so this is what we were saying before. This is the buffer zone. This is our direct conquest, and this is like this kind of infiltration in the market that will take some time, but eventually will be successful. All right, I have 30 seconds left. I just want to give you a teaser of what we're going to be seeing on Tuesday. So as I mentioned, today we've seen everything about decision-based models, and we're going to be talking about instead probabilistic models, okay, which apply to epidemic spreading. And we're going to be talking about given how likely is a certain disease to spread, then the disease will go around or will die out very soon, okay? But rather than having local choices, we will plug a probability on each node, and we will make a decision if the spreading carries on or not. Okay, lecture is over. Happy to take questions in person or also right now if you want. Question?
So, is there a way we can phrase like a node classification? Like, can we use the techniques we learned for node classification to do this type of thing as well? seems like there's some similarities.
Can we use node classification to do cascading? Yeah, great question. This is very similar to if you think about loopy belief propagation. Basically, what's happening here, every time someone is changing their mind or adopting something, you're sending a message to your neighbors. So there is definitely a parallel between the two. And the dual of the problem basically is instead of trying to see if someone will adopt a certain technology, you will try to predict if that's going to happen or not. So you can make that model from decision-based to prediction-based. Great question. Thanks. OK, thanks, everyone. Hey.
Is it possible to arrange office hour for